And when you do a DC sweep for this inverter, you are seeing this. Okay. So what is X? What is X in this curve? Yeah. Output. Okay. So the Y is VL. Right. So this line is VL. So what is this linear line? It is V in, right? You probably have another y-axis here, shows V in versus V in. It's y equals x. That's why it's a linear line, right? And so this curve can be obtained by running a DC sweep, and the intersection here is called VSP. Okay. So over here, does V in equal to VL? Are they equal? Yes, they are. This guy's V in, this guy's VL. They are sharing the same point, so they have the same voltage. And we define that point to be V switching point. That's a VSP, switching point of the inverter. And we hope that voltage to be 2.5 volts if you have a 5 volt power supply, if VDD is 5 volts. Okay, so we need to design that inverter to make it switch at 2.5 volts, usually. That's the ideal case, but most of the time you don't care. You just want to make the smallest size you can. If the switching point is at like 2.5, 2.54, 2.55, 2.6, nobody really cares. They care about how many transistors can integrate onto the chip. So they just use the minimum size for the width and length for all the transistors, pretty much. It's 5 nanometer technology, so all the transistors, the length are at 5, and they try to use a 5 for their width as well if it's just a pure logic. And you don't have to run a lot of current in it. So you don't have to make the transistor to be very big or very wide. So for this case, we are learning how to design a inverter that switches at 2.5 volts. So we know V in equals VL. Okay, and this is just one channel for DC current. So it's pretty much ISD. Sorry, for PMOS is ISD, for NMOS is IDS. They're the same current. And we can use a square law equation to find out VSP. Okay, so for the PMOS, you can use a square law equation to calculate its ISD, which is KPP, which is 40 microamps per V square. It's a constant, you can find from the textbook, over 2, and width over length. VGS or VSG in PMOS, right? VSG minus VTHP. So VSG here, the voltage difference between S and G is VDD minus V in, and V in is VSP, so we just use VDD minus VSP. At the moment, it's switching, okay? It's VDD minus VSP, which is VSG minus VTHP square. And that's channel current or source string current of the PMOS. That equals the string source current of the NMOS, which is KPN over 2 W over L. So these are PMOS is W and L, this is NMOS. And you are looking at VGS in this case. So G is V in, so V in is VSP in this case. So you are getting VSP minus VGS is VSP. So VSP directly minus VTHN square. To simplify it, we use another letter here. It's beta P, and this is beta N to represent these numbers, these constants, eventually you're getting beta p over 2 VDD minus VSP minus VTHP equals beta n over 2 VSP minus VTH n square. So n, the 2 got cancelled. You're getting beta p over beta n. Or beta n over beta p. Let's move this one to the right hand side of the equation. So that equals beta n over beta p, and move this one to this side, which is VDD minus VSP minus VTH p square over VSP minus VTH n square. Okay. Square root on both sides of the equation. So VDD minus VSP minus VTH p over VSP minus VTH n equals square root of beta n over beta p. Okay. So we're calculating VSP, keep in mind. And next, so move this one to the other side of the equation. It's going to be VDD minus VSP minus VTHP equals beta n over beta p, VSP minus VTHN, right? And we can see that here's another VSP, so we can factor that out by combining them. So we're getting VDD minus VTHP, which is this and this, and plus these two, okay, which is beta n over beta p times VTH n. We change the sign here because this is the minus. We move to the left, change it to a plus sign here. Okay, equals this plus this, which is VSP beta n over beta p plus 1. All right, let's see if I'm getting this right. Seems to be correct. Yeah, that's right. So VSP finally equals this one divided by this. VDD minus VTHP plus these are all constants, aren't they? Let's plug in the values into it. So for example, and we hope this one to be 2.5 volts, right? And then we are designing the size of the transistor by getting a value here. So the ratio of the N and P MOSes. Right? This is what we desired, right? And then we calculate back to find out the width and length of the transistor. So assuming that VSP is 2.5 volts, and this becomes 5 volts, which is VDD minus VTHP, which is 0.9 volts in the long, it's called long channel technology in the textbook. It's a 1 micrometer technology. It's just the educational model in the book. Okay. VTHP, the PMOS threshold voltage is 0.9 volts plus this parameter times 0.8 volts over this one plus 1. Okay. We can easily calculate this guy, which is very close to 1. That interesting? So if you want to design a CMOS logic gate and make a switching point in the middle, and you want these constants, the value here and value here, to be equal for the PMOS and NMOS, to be equal. Does that mean that you want to have the same width and length for the PMOS and NMOS? If you want to make these two equal, do you need the same width and length for the PMOS and NMOS or not? The same ratio. The KPP and KPNZ are different. Okay? The ratio, okay? So this one, so basically if this ratio is 1, beta n should be beta n equals beta b, p. No problem here, right? Which is KPN times WN over LN equals KPP WP over LP. So it's given that KPN is 120 microamps per V square, and KPP is 40 microamps voltage square. So this KP thing, this parameter, carries a constant. It's called mobility of the particles. I think in the model file it's a U something. In there U0 or something else, I forgot. So it's a mobility of the particles. So in the N-type material, in the channel, okay, in the channel, a positive voltage here for the gate attracts electrons to the channel. So the charge is moving in the NMOS transistor, the N-type transistor is actually electrons. But in the P-type transistor, if you have a negative negative voltage, it's P plus, right? It's a PMOS. So you usually bias S and G using a positive voltage, but you do have a cathode connected to the gate, right? So in that case, actually the holes in the P substrate will be attracted to the channel and form the channel. So the channel in the PMOS transistor is purely holes. But the channel here in the NMOS transistor is electrons. Does that make sense? Okay, so very quick check here. So if we want to run the hose from source to drain, which terminal should have a higher voltage potential for the PMOS? Which one is shorted to the higher potential to run the particles in the channel, to create the current, electrical current in the channel? Source, okay? So that's why you have PMOS sources connect to VDD, okay? Keep in mind, for PMOS, source is on the top, it's connected to VDD. For NMOS, source at the bottom is shorted to ground. Okay? And the reason that these two parameters are different is because electrons has higher mobility than holes. Just remember that, okay? So electrons are moving faster and easier than holes. So you can see this, the same number of VGS or VSG, the NMOS is getting you a bigger current, okay? So in this case, how do you want to design your W here, or the ratio here, to make it equal? It's very simple, right? Middle school math. So KPN, or KPP. KPP is, let's do KPN, it's easier. So KPN is 3 times of KPP, right? Just looking at these numbers. So KPN is 3 times of KPP. So cancel KPP on both sides. Okay, that's how I can make it equal. So which one should be larger? Which one should be larger ratio to reach this purpose, to make it to switch at 2.5 volts? Which one should be larger? Which transistor should be larger? The PMOS. The PMOS should be larger, right? Because they are equal. So this one, assuming we are using the same length to reduce the size, because you don't want to change both at the same time, is waste of area on the chip. Just keep this as the smallest possible, the smallest size on the chip or from technology, and keep changing the W here, right? So 3WN equals WP, so we need a WP to be bigger because 3 times WN is WP. So WN is definitely smaller than WP. So in that case, if you want to make that this guy switch at 2.5 volts, if we are using, for example, 1 micron, it's a 1 micrometer technology. It's 1 micrometer for the length. Depends on how much current you need from the circuit, right? But just keep in mind, if you want to make a switch at 2.5 volts, WP should be 3 times larger than WN. That's the conclusion here, okay? So I think I'm gonna let you guys do quiz 7 at 11:55. 11:50 probably. I don't know. Just let you guys know. Okay, let's try it on LT Spice, see if that works. Let's use a 1 micron technology. So I'm keeping the simulation file and the model file in the same directory on the textbook, on the desktop, and it's n_1u for the NMOS, p_1u for the PMOS. F2 to grab the components. So remember that for PMOS in LT Spice, you have to rotate it and measure it. It's okay for this technology because it's symmetrical for the PMOS on both sides. The source and drain are identical, but you just remember that the way they design it is the gate is closer to the source. So if you can see here, gate is over here, so the source is on the top. Okay. So this is P. And DDD. Make it longer so I can connect the body of it to here, and the body of it to here. And naming that V out. V. Okay. And this guy should be V in. Right. So I'm gonna sweep it, and I'm gonna ground it. So this I give a 0, so I'm gonna do a DC sweep for it. So I want to dot include. Let's do a DC sweep first. Is that V1? V1. Do I need a 0? V1 0 and from 0 to 5 volts. Wait, still couldn't press enter here. See if that works first. Hopefully I have a correct DC sweep. DC transfer characteristics. So I don't need 0 here, seems like. Is that correct? Now it works. So if I probe it, you can see switching at, what's the voltage here? It's not definitely not 2.5. If I measure it, I can probably zoom in. Okay. So what's the switching point? 1.95, 1.96 volts. Okay. Is it switching too early or too late? Too early, right? Too early means what? Switching to where too early? Seriously? It's going down, right? It's rushing to where? To ground, right? This is rushing to ground too early. Why? Who is pulling that point to ground? Yeah, the NMOS is pulling that to ground, which means what? Means you have a strong NMOS. You have a strong NMOS. Strong means you have a wider channel. So you can imagine that it's just like two people, one on the top, one on the bottom. Who is stronger can pull it down to ground early or pull it up early. So because NMOS has a higher mobility for the electrons, and since we haven't changed the width and length yet, I think by default they just give a default value to the width and length in LT-SPICE. They must have equal width and length or ratio for PMOS and NMOS, right? So that's why I haven't changed the size, the ratio of the PMOS yet. So that's why it's weaker, because the mobility of the holes are lower than the mobility of the electrons in NMOS. So you want to make the PMOS stronger or weaker to pull it to the right hand side. Make the PMOS what? To make it stronger, okay? So let's modify it here. Usually the minimum width and length that I can fabricate over here is 1 micron. That's a model file, a huge technology. But let's just keep 2 times, still use the lambda rule, then it's going to be 2 micron. Right? Let's use 2 micron for the length. And width, let's use 10 micron, for example. for the NMOS, right? Is that NMOS? Oh, that's PMOS. That's just 20 micron, okay? Hmm. 30 micron, for example. It's not visible, so I have to do a control right click. Control right click. Keep in mind, you have to press control at the time you are pressing right click. And you want to show the dimension of it. So double click and check this box. So it's going to make it visible. You can see the size of the transistor. So the length is 2 micron and the width is 30 micron. And for the NMOS, if you want to switch it at 2.5 volts, assuming that we are still keeping the same length for the NMOS, what's the width should be for the NMOS to make it switch at 2.5 volts? Does that make sense for everyone? Because the PMOS should be 3 times larger than the NMOS in order to switch at 2.5 volts. And the same thing, we need to do a control right click, right? And now let's rerun it. Pretty much 2.5 now, right? Let's probe it and see. .50. Okay. Now, if I want to switch it at this point or on the right hand side, what should I do? So so what's happening is, because at the very beginning, the voltage output here is high, and Vout is connected to the output, the drain of the NMOS and PMOS. Okay, so if you want to switch it at a later time, which means your PMOS is holding the voltage or pulling the voltage up to the VDD for a longer time. Does that make sense? For example, if you switch it here, like this curve, you move it, you shift to the right like this. So it's switching here, for example. So which means your PMOS is holding the charge or pulling the output to VDD for a longer time. So I have a strong PMOS. If you make a strong PMOS, it's going to switch at a later time. Okay? Let's make it 10 times larger. Make sense? So you know that by changing the width of the transistors, you can make that transistor powerful. Okay, you can make it powerful, more powerful, by giving more current through the channel to the output. So if you want to make a strong transistor to reduce the time delay or to drive a big capacitor, you should increase the width to just make a bigger pipe on the top. Just think about this transistor, just a pipe. Okay, just increase the diameter of the pipe so you have more water flowing down. Okay, so that's the concept here. Okay. Let's spend another 5 minutes to talk about AOI logic. For this circuit, the layout looks like this. Power, drain, ground, input, output. In this one, the layout, you have 3 transistors in the middle, or 2 transistors on the top in parallel. So we prefer the more metals in the middle and less metals in here, because we might route a lot of traces in here. So to reduce the chance of shorting any circuits in here. Okay, and this one makes these two in series. Okay, and that's 2 gates. That's A, B. This is metal. This is Y equals A. It's a NAND gate. Okay, for NOR gates, you got 2 PMOSes on the top in series and 2 NMOSes. And here's VL or Y. Let's use Y. Okay. In series, A, B, and that's Y. And you can find out whenever you have under the bar, because it's always inverting the final signal. You can just see, like, if you use this type of circuit, it's always inverting your signal. So you always have a bar on the top. And if the logic has an OR here, has an OR operator, you need 2 series PMOSes and 2 parallel NMOSes. It's like AND or an inverter. Okay, so that's why it's called AOI. If you look at this one, this is A, B, not. So it's an AND or inverter, see? And if you have an AND logic under the bar, the AND logic under the bar, you have PMOSes in parallel on the top and NMOSes in series at the bottom. So if you can remember that, we can design a lot of different circuits. So for example, starting with a very simple one, if we have A, B, C, NAND, okay, 3 inputs and NAND, okay, AND together and then NOT, right? And if you're using the same method here, the circuit should look like what? Keep in mind, under the bar, if you have an AND logic, you need parallel PMOSes and series NMOSes. Okay, so this circuit is very simple. It's basically just the 3 parallel PMOSes on top. Okay, A, B, C. And that's output. What about this? You have under the bar, you have OR logic. So you want to put, so always think about the NAND gate, the basic NOR gate and NAND gate. Okay, for OR logic under the bar, you need the series PMOSes on top and parallel NMOSes at the bottom. So this one will be doesn't matter which one's A, which one's B and C. They just need to make the schematic and layout match with each other. But when you name it, it doesn't matter. Or which one connect to which, doesn't matter, because all the 3 parallel NMOSes are equal. They're identical. Does that make sense? So start learning more structures and more complicated logic equations and their layout in the future. Okay, on Monday.
Let's do the quiz.